What if everything you think you know about time is just the tip of an unimaginably vast iceberg? Picture this. Right now, as you watch this, your past might still be unfolding somewhere. Your future already exists in another layer of reality. And the present moment you're experiencing could be just one thread in a cosmic tapestry of time dimensions we can't even perceive. This isn't science fiction, it's what cutting-edge physics suggests might be happening all around us. For centuries, we've treated time as a simple, one-way street. But what if it's actually a sprawling, multidimensional labyrinth? Today, we're diving deep into 30 mind-blowing theories that reveal time's hidden layers, from Einstein's revolutionary ideas about frozen space-time to bizarre quantum experiments where the future seems to influence the past. You'll discover how black holes might be natural time machines, why some scientists think time doesn't exist at the smallest scales, and how your consciousness could be literally creating the flow of time as you experience it. Each of these theories will challenge everything you thought was true about reality. So if you're ready to have your mind stretched beyond its limits, keep watching, because by the end of this journey, you'll never look at a clock the same way again. Now, let's peel back the first layer of time's mystery with the block universe theory. Imagine the entire history of the universe, every event, from the Big Bang to this very moment, laid out like a giant, unchanging loaf of bread. That's the essence of this idea. Time isn't flowing like a river but exists all at once, with past, present, and future stacked together in a four-dimensional block. Einstein's theory of relativity is the backbone of this mind-bending concept. It showed that time is flexible, stretching or compressing depending on how fast you're moving or how strong gravity is around you. What you experience as now might be someone else's then if you're moving at different speeds. This shatters our everyday notion of a universal present, suggesting that your childhood, your next birthday, and even the heat-death of the universe are all equally real, just at different coordinates in space-time. Think of it like a DVD where every scene exists simultaneously, but your consciousness only plays one frame at a time. The block universe doesn't just challenge our intuition, it forces us to ask, if time is already written, what does that mean for free will, destiny, or the very nature of reality itself? Now, let's take a step deeper into the puzzle of time with two competing visions, Eternalism and the growing block model. Picture Eternalism as a vast, frozen landscape where every moment, your first steps, the fall of the Roman Empire, and even the distant future exists simultaneously like frames in an endless film reel. This view aligns neatly with the block universe, treating past, present, and future as equally real, just different points in spacetime's unchanging structure. But not everyone agrees. Enter the growing block model, which imagines time as a construction site where the past and present are solid, finished floors, while the future remains an empty blueprint. Here, reality isn't fixed, it's actively building itself, moment by moment. Philosophers have wrestled with these ideas for centuries. Eternalism offers a tidy, deterministic universe, but it raises tough questions about free will. If the future is already out there, are our choices an illusion? Meanwhile, the growing block feels more intuitive, preserving the sense that the future is unwritten, but it clashes with relativity's insistence that time is flexible. Quantum mechanics throws another wrench into the debate. Particles in superposition seem to defy classical notions of time, existing in multiple states until observed. Does this mean reality only solidifies when we look, supporting the growing block? Or does quantum entanglement's spooky action at a distance hint at a deeper, timeless fabric favoring eternalism? The truth might lie somewhere beyond both, or perhaps our human brains just aren't wired to grasp time's true nature. Either way, these theories remind us that time isn't just a ticking clock, it's a frontier where physics and philosophy collide. Now let's shift our focus to something we all experience but rarely question, the one-way flow of time. Why does an egg splatter when it hits the floor but never reassemble itself? This everyday mystery points us to the arrow of time, a concept deeply tied to entropy, the measure of disorder in the universe. Picture a sandcastle on the beach. Left alone, wind and waves will scatter its grains, never arranging them back into towers and walls. That's entropy at work, always increasing, driving time's irreversible march forward. But here's the puzzle. If entropy always grows, why did the universe start in such a remarkably ordered, low-entropy state? Think of it like a deck of cards perfectly sorted by suit and number. Shuffle it once and it's disordered. Shuffle it 1,000 times and it'll never return to that pristine order unless someone deliberately rearranges it. So who or what stacked the cosmic deck in our favor? Some physicists point to the Big Bang as that initial moment of perfect order, while others speculate about deeper laws or even multiple universes with different starting conditions. This isn't just abstract science. Entropy shapes everything from aging to black holes. Your coffee cools because heat disperses, never spontaneously concentrating back into your cup. Stars burn out because energy spreads irreversibly. Even memories rely on entropy. Your brain records the past because disordered neurons can't unscramble themselves. Yet, despite its grip on reality, entropy doesn't explain why we perceive time's flow so vividly. Is it just a side effect of our low entropy beginnings, or is there more to the story? The arrow of time remains one of physics' greatest enigmas, a reminder that the simplest questions, like why we remember yesterday but not tomorrow, can lead to the deepest mysteries of the cosmos. Now, let's peel back another layer of the cosmic onion and consider a radical idea. What if time isn't a fundamental part of the universe at all? Instead of being woven into the fabric of reality from the start, time might emerge from something deeper, like a wave rising from the ocean. This is the heart of Theory 4, where time isn't a backdrop but a side effect of quantum interactions. Picture spacetime as a digital image. Zoom in far enough and you'll see it's made of tiny pixels, discrete chunks of reality. That's the vision of loop quantum gravity, a framework suggesting that at the smallest scales, time dissolves into a network of interconnected loops. Imagine trying to watch a movie where each frame is scrambled. You wouldn't see a flowing story, just flickering chaos. Similarly, at the quantum level, time might lose its smooth, continuous nature, becoming a jumble of events without a clear order. This idea turns our everyday experience upside down. We perceive time as a river always moving forward, but if time emerges from quantum processes, that flow could be an illusion, like the apparent motion of a flipbook. Some physicists argue that what we call time is just a useful approximation, a way to make sense of the universe's underlying complexity. The implications are staggering. If time isn't fundamental, then the Big Bang might not be the beginning of time but a phase transition, like water freezing into ice. Even the arrow of time could be a consequence of how these quantum building blocks interact, rather than a law written into the cosmos. So next time you check your watch, remember, those ticking seconds might not be the heartbeat of the universe, but a shimmering mirage on the surface of something far stranger. Now, let's stretch our minds even further with a theory that feels straight out of science fiction, except it's rooted in cutting-edge physics. Theory 5 introduces the holographic principle, a mind-bending idea that our experience of time might be nothing more than a shadow cast by a higher dimensional reality. Think of it like this. Imagine a movie projected onto a flat screen. The images move, the story unfolds, but everything you see is actually encoded on a two-dimensional film strip. The holographic principle suggests something similar about our universe. What we perceive as time and space could be a three-dimensional projection of information stored on a distant, higher-dimensional surface. This idea comes from a discovery called the AD/CFT correspondence, a mathematical bridge between two seemingly unrelated theories. On one side, you have gravity and spacetime as described by general relativity. On the other, you have quantum field theory, which governs particles and forces. The holographic principle shows that these two frameworks can be equivalent, like translating a book into another language without losing its meaning. The implications are staggering. If time is just a projection, then the real universe might be timeless, with past, present, and future existing simultaneously in a higher dimension. It's as if our entire cosmic history is frozen like frames in a film reel, and what we call now is just the projector's beam illuminating one slice at a time. This could solve one of physics' biggest headaches: how to reconcile gravity with quantum mechanics. By treating space-time as an emergent hologram, the holographic principle might finally unite these two pillars of modern science. So the next time you feel the seconds ticking by, consider this. Your experience of time might be as illusory as the images on a movie screen, with the true action happening somewhere far beyond our perception. Now, let's take a detour into one of the wildest corners of physics, where time doesn't just flow forward but can twist back on itself like a tangled ribbon. Theory 6 brings us to closed timelike curves, or CTC, the scientific term for time loops allowed by Einstein's general relativity. Yes, you heard that right. Time travel might not just be for movies. Picture this: a Tipler cylinder, a hypothetical structure so dense and spinning so fast that it warps space-time into a loop. If you traveled around it in just the right way, you could end up back where you started, not just in space but in time. Or consider Gödel's rotating universe, a solution to Einstein's equations where the entire cosmos spins, creating paths that circle back to the past. These aren't just thought experiments, they're mathematically valid under relativity. But here's the catch: what happens if you go back and, say, accidentally prevent your own birth? That's the infamous grandfather paradox, where a time traveler's actions erase their own existence. Physics offers a few escape routes. One idea is the Novikov self-consistency principle, which suggests the universe would conspire to stop contradictions. Maybe your gun jams or you miss the shot. Something would always keep the timeline intact. Another twist: quantum mechanics might allow multiple outcomes, where every possible action branches into parallel timelines. So instead of erasing yourself, you just spin off into a new reality where history plays out differently. Whether these loops are possible or just mathematical quirks, they force us to ask: is time as rigid as we think, or is it more like a river with whirlpools and eddies? The answer could rewrite not just physics, but our very understanding of cause and effect. Now, let's stretch our imagination even further, into a reality where every choice you make doesn't just alter your future, but creates entirely new universes. Theory 7 dives into the multiverse and branching time, a mind-bending idea rooted in Hugh Everett's many worlds interpretation of quantum mechanics. Forget a single timeline here. Every possible outcome plays out somewhere in some universe. Think of it like flipping a coin. In our world, it lands heads or tails. But in the multiverse, both outcomes happen, just in separate, parallel realities. This isn't just sci-fi. Quantum mechanics suggests particles exist in multiple states until observed, and Everett argued that observation doesn't collapse those possibilities, it splits them. Your decision to drink coffee this morning, one universe where you did, another where you chose tea, and countless others where you did something entirely unexpected. Pop culture loves this idea. Remember Doctor Strange navigating infinite timelines in Multiverse of Madness? That's a flashy Hollywood take, but the real science isn't far off. The difference: in Everett's multiverse, there's no sacred timeline to protect, just an ever-expanding tree of realities, each equally valid. But here's the twist: if every possibility exists, does anything ever truly end? In one universe, that missed train leads to a chance encounter. In another, it's just another Tuesday. The implications are staggering, blurring the line between fate and free will. Are we the authors of our lives, or just one thread in an infinite tapestry? Whether you find it liberating or overwhelming, the multiverse forces us to rethink not just time, but the very nature of existence. And if that doesn't make your head spin, just wait, there's a universe out there where it already did. Now, let's step into a world where time itself takes on a shape, not just flowing forward, but crystallizing into patterns that repeat like the ticking of an impossible clock. Theory 8 brings us to the mind-bending concept of time crystals, a discovery so groundbreaking it earned a Nobel Prize. Unlike ordinary crystals, where atoms arrange themselves in repeating patterns in space, time crystals repeat their structure in time. Imagine a snowflake that doesn't just sit still but pulses in a never-ending dance, cycling through its form over and over without any energy input. This isn't science fiction. In 2016, physicist Frank Wilczek proposed the idea, and by 2017, scientists had created time crystals in the lab using chains of ions or defects in diamonds. The wild part, these structures defy one of physics' most sacred principles, time symmetry. Normally, the laws of physics work the same whether time runs forward or backward. But time crystals break that symmetry, creating a system that's inherently out of sync with the universe's usual rhythm. Why does this matter? For starters, time crystals could revolutionize quantum computing. Their stability and resistance to external noise make them ideal for preserving quantum information, potentially solving one of the field's biggest hurdles to coherence. Picture a quantum computer that doesn't lose its data to random disturbances, thanks to these time-looped marvels, but the implications go even deeper. If time can crystallize, what else might be possible? Could there be hidden layers of temporal order we've yet to uncover? Time crystals challenge us to rethink not just how we measure time, but how it fundamentally behaves. And as we peer into this strange new frontier, one thing becomes clear. The universe still has plenty of surprises up its sleeve. Speaking of surprises, our next theory takes us even further into the unknown, where time might not exist at all. Now, let's venture into a realm where time itself might not even exist, at least not in the way we think. Theory 9 introduces us to the Wheeler-DeWitt equation, a revolutionary idea that strips away time entirely from the fabric of reality. This equation, born from the marriage of quantum mechanics and general relativity, describes the universe in a way that doesn't include time as a variable. It's as if the universe is frozen in a single, unchanging moment, a cosmic snapshot where past, present, and future are all one and the same. So why does this matter? The Wheeler-DeWitt equation forces us to confront what physicists call the problem of time. In our everyday experience, time flows like a river, carrying us from one moment to the next. But at the deepest levels of reality, time might just be an illusion, a trick of perception rather than a fundamental feature of the universe. Think of it like watching a movie. The film strip itself doesn't move, it's just a series of still frames. Our brains stitch those frames together to create the illusion of motion. Could time work the same way? Some of the brightest minds in physics, like Julian Barber and Carlo Rovelli, argue exactly that. They suggest that what we perceive as time is actually just relationships between events, a cosmic network of cause and effect without any true flow. This idea turns our intuition upside down. If time isn't real at the most basic level, why does it feel so undeniable? The implications are staggering. If the Wheeler-DeWitt equation is correct, it could mean that the universe operates in a timeless state, with change and motion being nothing more than emergent properties. This challenges not just our understanding of physics, but our very sense of existence. Are we just patterns in a timeless void, or is there something deeper at play? As we grapple with these questions, our next theory pulls us even further into the unknown, where time might not just be an illusion, but a dimension we've yet to fully comprehend. Let's shift gears and explore a theory that flips our everyday experience of time on its head. Theory 10 brings us to the B theory of time, a perspective that challenges the very notion of time as something that flows. Unlike the A theory, which treats the past as gone, the present as real, and the future as uncertain, the B theory argues that all moments in time are equally real. Think of it like a cosmic photo album where every page exists simultaneously. Your birth this very second and events 1,000 years from now are all equally present in the grand structure of space-time. This idea isn't just philosophical speculation. It's rooted in Einstein's theory of relativity, which treats time as a fourth dimension, no different from space. Just as you can move left or right in space, all points in time, past, present, and future, are fixed in this four-dimensional block. There's no special now that moves forward. Instead, every moment is like a frozen frame in an endless film reel. But here's where things get tricky. If the B theory is true, how do we explain our vivid sense of time passing? Why does it feel like we're moving through life rather than statically existing at every point in our timeline? Some philosophers suggest this is a quirk of human consciousness, a kind of illusion crafted by our brains to make sense of the world. Others argue that free will becomes a puzzle under B theory. If the future is already out there, fixed in the block universe, do our choices even matter? The debate rages on, with some scientists pointing to quantum mechanics as a possible bridge between B theory and our lived experience. Could our perception of time's flow be a side effect of quantum uncertainty, where multiple possibilities exist until observed? Or is the B theory simply too cold and deterministic to capture the richness of human existence? As we wrestle with these questions, one thing becomes clear: time is far stranger than our intuition suggests. And with that, we're ready to dive into an even more radical idea where spacetime itself might be built from tiny, discrete pieces of causality. Now, let's zoom in on a theory that breaks spacetime down to its most fundamental building blocks. Theory 11 introduces us to the causal set theory, a radical idea that suggests the universe isn't smooth and continuous, but instead made up of tiny, indivisible atoms of causality. Picture spacetime as a vast cosmic network where each point represents an event, and the connections between them define cause and effect. This theory flips the script on how we usually think about time and space. Instead of treating them as a flowing river or a static block, causal set theory sees them as a collection of discrete moments linked by relationships. Imagine a family tree where each generation is connected to the next, except here, it's not people but events that form the links. The order in which these events happen isn't dictated by some external clock, but emerges purely from how they're causally related. What's truly mind-bending is how this approach might uncover hidden dimensions of time. If spacetime is granular at its core, like a pixelated image, then the smooth flow we experience could be an illusion created by the sheer density of these causal atoms. Some physicists speculate that at the smallest scales, time might not even behave linearly. Instead, it could branch, loop, or even exist in layers we can't perceive. But how does this hold up against reality? Causal set theory offers a way to reconcile quantum mechanics with gravity, two forces that famously refuse to play nice in traditional frameworks. By focusing on the relationships between events rather than a rigid spacetime backdrop, it opens the door to a universe where time isn't a fixed dimension but something more fluid and dynamic. Of course, this raises big questions. If time is just a web of cause and effect, what does that mean for free will or the arrow of time? Could there be hidden causal layers operating beyond our perception? While the math is still evolving, one thing's certain: causal set theory challenges us to rethink time not as a stage but as the very fabric of the play itself. And with that, we're ready to explore another twist in the cosmic puzzle, a theory where the universe resets itself in a cycle of collisions and rebirths. Now, let's step into a cosmic cycle where the universe doesn't just begin once, it's reborn over and over. Theory 12 takes us into the ekpyrotic universe, a bold idea that reimagines the Big Bang not as a singular explosion, but as a collision between multidimensional membranes or brains lurking in higher dimensions. Picture this: our entire universe exists on one of these brains, floating like a sheet in a vast, hidden space. Every few trillion years, another brain drifts close and smashes into ours, unleashing enough energy to reset time itself. Instead of a one-time Big Bang, this collision becomes a cosmic reset button, wiping the slate clean and starting the universe anew. How does this compare to the traditional Big Bang? While the classic model paints time as a straight line stretching from a single explosive beginning, the ekpyrotic universe turns time into a loop. Each collision isn't just a rebirth, it's a replay with matter, energy, and even the laws of physics recycling into a fresh cosmic era. But here's where extra dimensions come into play. In string theory, these brains exist in a space with more than the 3 dimensions we experience. The collisions between them could explain why time appears cyclical on a grand scale. If time is woven into these higher dimensions, it might not flow in a straight line at all. Instead, it could fold back on itself, creating endless cycles of creation and destruction. Critics ask, where's the evidence? While we can't yet observe these brain collisions directly, the ekpyrotic model offers solutions to puzzles like the universe's startling uniformity. Instead of relying on inflation, a rapid expansion after the Big Bang, this theory suggests that the slow, steady approach of brains before collision could naturally smooth out the cosmos. So, what does this mean for time? If the ekpyrotic universe is real, then the arrow of time might not be an irreversible march toward entropy. Instead, each collision could flip the script, making time's flow as cyclical as the seasons. It's a vision of the cosmos where endings are just beginnings in disguise. And with that, we're ready to confront a darker possibility, a universe where time doesn't just loop but one day stops altogether. But before we explore the idea of time stopping altogether, let's take a moment to consider what that would even mean. Theory 13 forces us to confront the most unsettling possibility of all, a universe where time itself comes to an end. Imagine a clock that never ticks again, not because it's broken, but because time has simply run out. One leading scenario is the heat death of the universe, where entropy reaches its maximum. Stars burn out, black holes evaporate, and all energy disperses into a cold, uniform void. In this frozen state, nothing changes, no motion, no reactions, just an endless static silence. Without change, time loses all meaning. It's not just that the universe ends, it's that time itself ceases to exist. Then there's vacuum decay, a far more violent finale. Picture a bubble of true vacuum forming somewhere in space, expanding at the speed of light. As it spreads, it rewrites the very laws of physics, tearing apart atoms and space-time itself. In an instant, everything we know, past, present, and future, could vanish without warning. Time wouldn't just stop, it would be erased. But why would time end? The answer lies in the fundamental nature of the cosmos. If time is tied to change, as many physicists argue, then a universe where nothing changes is a universe without time. And if the fabric of reality is unstable, as vacuum decay suggests, then time might not just fade away. It could be ripped from existence. The stakes couldn't be higher. If time ends, so does history, memory, and the very concept of cause and effect. No more beginnings, no more endings, just an absolute, irreversible stillness. It's a chilling thought, but one that forces us to ask, is time truly eternal, or is its existence as fragile as the universe itself? And with that, we turn to a theory that flips the script entirely. String theory's hidden dimensions, where time might not be what we think at all. Now, let's unravel a theory that bends our understanding of time in ways you've never imagined. String theory, one of the most ambitious frameworks in physics, suggests that our universe isn't just made up of the 3 spatial dimensions we experience, length, width, and height, or even the 4th dimension of time. Instead, it proposes there could be 10 or more dimensions, all curled up and hidden from our everyday perception. Here's where it gets wild. Some of these extra dimensions might not just be spatial, they could be layers of time itself. Think of time not as a single arrow moving forward, but as a complex, multi-dimensional fabric where past, present, and future could intertwine in ways we can't yet comprehend. This idea challenges everything we think we know about cause and effect, opening the door to possibilities like parallel timelines or even moments where time folds back on itself. A key piece of this puzzle is something called Calabi-Yau manifolds. These are intricate, six-dimensional shapes that string theory suggests could be the hidden geometry of the universe's extra dimensions. If these shapes exist, they might determine how time behaves at the most fundamental level, perhaps even allowing for multiple flows of time or pockets where time operates differently. But there's a catch. Testing these ideas is incredibly difficult. Unlike other theories that can be probed in particle colliders or astronomical observations, string theory's extra dimensions and their potential temporal layers are so tiny and elusive that we currently lack the tools to detect them directly. Some physicists argue this makes the theory untestable, while others hold out hope that future breakthroughs like quantum gravity experiments or new mathematical insights might one day reveal these hidden dimensions. So, what does this mean for our understanding of time? If string theory is correct, time might be far richer and more mysterious than we ever realized, a tapestry woven from multiple threads, each representing a dimension we're only beginning to glimpse. And with that, we're ready to dive into another mind-bending idea, quantum retrocausality, where the future might influence the past. Now, let's step into a world where the future reaches back to shape the past. The transactional interpretation of quantum mechanics flips our everyday logic on its head, suggesting that events in the future can ripple backward to influence what happens now. Imagine throwing a ball, but somehow where it lands changes how you threw it in the first place. That's the kind of mind-bending possibility we're dealing with here. At the heart of this idea is something called the delayed choice experiment. Picture a photon, a tiny particle of light traveling through a setup where it can take two paths. Normally, we'd expect the photon to choose one or the other. But in this experiment, scientists can wait until after the photon has already decided its path before choosing how to measure it. Astonishingly, the measurement made later seems to affect which path the photon took earlier. It's as if the future is whispering to the past, tweaking the rules of cause and effect. This isn't just a quirky lab result. It hints that at the quantum level, time might not be the one-way street we're used to. Instead, particles could be sending signals both forward and backward in time, creating a kind of handshake between past and future. Some physicists argue this is how quantum events settle into reality through a negotiation across time itself. Of course, this raises big questions. If the future can influence the past, does that mean events are predestined? Or is reality more like a conversation where the past and future constantly adjust to each other? The transactional interpretation doesn't have all the answers, but it opens a door to a universe where time is far more fluid and far stranger than we ever imagined. And with that, we're ready to explore another twist in the fabric of time, the idea that some timelines might be self-correcting, avoiding paradoxes at all costs. Now, let's untangle a fascinating idea that keeps time travel from spiraling into chaos, the Novikov self-consistency principle. Picture this. You hop into a time machine, determined to change history, but no matter how hard you try, the universe has a way of keeping things in line. That's the core of this principle. Time travel might be possible, but only if it doesn't create paradoxes. Think of it like a cosmic safety net. If you traveled back to prevent your parents from meeting, somehow fate would intervene. Maybe your actions accidentally bring them together instead. The universe, in this view, has a built-in rulebook. Any event that could create a contradiction simply won't happen. It's not that time travel is impossible, it's that the timeline heals itself, bending to avoid inconsistencies. This idea isn't just science fiction. Physicist Igor Novikov proposed it as a serious solution to the infamous grandfather paradox. If you tried to kill your younger grandfather, the principle suggests something would stop you: a gun jamming, a sudden change of heart, or even a stray banana peel. The past isn't a sandbox for reckless edits. It's a locked puzzle where every piece must fit perfectly. But here's where it gets even more intriguing. Some theories suggest that self-consistency doesn't just prevent paradoxes, it might actively shape reality. Imagine every time travelers' actions were always part of history, subtly woven into the fabric of events. What looks like free choice could actually be the universe ensuring its own coherence. Of course, this raises questions. Does this mean our futures are set in stone? Or is there flexibility within the rules, allowing for small changes that don't break the timeline? The Novikov principle doesn't claim to have all the answers, but it offers a compelling vision. One where time travel isn't about rewriting history, but discovering how tightly the threads of cause and effect are already tied. And with that, we're ready to explore an even bolder idea. What if time isn't just one dimension, but two? Now, let's stretch our minds even further with a theory that reimagines time itself, not as a single dimension, but as two. Welcome to the two-time theory, where the fabric of reality might have not just one arrow of time, but two. Imagine time as a sheet of paper with not just a left-to-right timeline, but also an up and down one. This isn't just a wild idea, it's a serious attempt to solve one of physics' biggest puzzles: why quantum mechanics and relativity don't play nicely together. Quantum mechanics deals with the bizarre behavior of tiny particles, where things can be connected across vast distances instantly, what Einstein called spooky action at a distance. Relativity, on the other hand, gives us the smooth, predictable curvature of spacetime. The two-time theory suggests that adding an extra temporal dimension could bridge this gap. Picture a five-dimensional universe, 3 dimensions of space plus 2 of time. In this setup, what looks like weird quantum connections might just be particles interacting along this hidden second time dimension, unseen but deeply influential. This idea isn't just about making the math work. It could explain why particles seem to know what their distant partners are doing without any signal passing between them. If time has 2 layers, those entangled particles might be sharing information along the second dimension, bypassing the speed of light limit that relativity imposes. It's like 2 people communicating not by shouting across a room, but by passing notes through a hidden back channel. Of course, this raises big questions. How would we experience a second time dimension? Would it feel like déjà vu or something stranger? And how could we ever test such a theory? For now, it remains a tantalizing possibility, one that hints at a universe far more intricate than our everyday experience suggests. But if it's true, it could finally unite the warring worlds of quantum weirdness and cosmic order. And that brings us to our next mind-bending idea, the presentist view, where only the here and now is real. Now, let's step into a completely different way of thinking about time, one that feels intuitive but clashes with some of physics' biggest ideas. The presentist view argues that only the present moment is real. The past gone, the future not here yet. It's just you right now in this fleeting slice of existence. This might sound like common sense, but when you hold it up against theories like Eternalism, where past, present, and future all exist equally, it sparks a fierce debate. Eternalism, as we've seen, treats time like a frozen block where every moment is equally real. But presentism says no, time flows, and only what's happening now truly exists. Think of it like a spotlight moving across a stage, illuminating only one actor at a time. The rest are in darkness, waiting their turn. This feels right to us because it matches our lived experience. We remember the past and anticipate the future, but we only ever feel the present. But here's the problem. Relativity throws a wrench into this neat idea. Einstein showed that now isn't universal. What's present for you might be past or future for someone else moving at a different speed. If time is flexible, how can there be a single objective present? Presentists have scrambled to adapt, suggesting that maybe the present isn't a fixed point but a kind of local phenomenon, like a bubble of now that changes depending on your perspective. Some even propose tweaking presentism to work with relativity by treating space-time as a dynamic fabric where the present is constantly updating, like a live feed refreshing itself. It's a tricky balance, trying to keep the intuitive appeal of only now is real, while bending just enough to fit the weirdness of modern physics. So, is presentism doomed, or can it survive in a relativistic universe? That's still up for grabs, but one thing's clear: whether time flows or stands still, our perception of it shapes everything from philosophy to how we live our daily lives. And that brings us to another fascinating twist: the idea that time might not be absolute at all, but something far more fluid. Now, let's turn our attention to a theory that flips the script on how we think about time's very nature. The R-theory of time suggests that time isn't some absolute backdrop to the universe. It's relational, meaning it only exists in relation to events and objects. Picture it like this: time isn't a river flowing on its own. It's more like the ripples created by stones tossed into a pond. Without the stones, there are no ripples. Without events, there's no time. This idea isn't brand new. It traces back to the philosopher Gottfried Wilhelm Leibniz, who argued that time isn't a standalone thing but a way to describe the order of events. Think of it like a chess game. The moves don't happen in time. Time is the sequence of moves. If nothing changed, time wouldn't even make sense. Leibniz's view clashes with Newton's idea of absolute time, which treats it as a universal clock ticking away regardless of what's happening in the world. Fast forward to modern physics, and the R-theory finds surprising allies in quantum gravity research. Some theories, like loop quantum gravity, suggest that at the smallest scales, spacetime might be granular, made up of discrete atoms of reality. In this framework, time emerges from how these atoms interact. It's not fundamental but woven from relationships, just like Leibniz imagined. Even the Wheeler-DeWitt equation, a cornerstone of quantum cosmology, describes a universe without time at its most basic level, hinting that time might be a cosmic illusion that arises from deeper connections. So, what does this mean for us? If the R-theory is right, time isn't something that exists out there. It's a byproduct of change, a story we tell to make sense of how things unfold. This shifts how we think about everything from the Big Bang to the ticking of a clock, and it leaves us with a tantalizing question. If time is relational, what happens to our understanding of cause and effect, or even free will? That's a puzzle for another theory, but for now, let's keep unraveling the threads of time's hidden dimensions. Now, let's take a step into a world where the arrow of time might not be as one way as we think. Time-symmetric quantum mechanics flips our usual understanding of cause and effect, suggesting that quantum laws could work just as well backward as they do forward. Imagine a game of pool where the balls not only roll forward but also reverse perfectly, obeying the same rules either way. That's the kind of symmetry this theory proposes for the quantum realm. At the heart of this idea is the Aharonov-Bohm effect, a fascinating quantum phenomenon where particles are influenced by electromagnetic fields even when they never directly interact with them. Here's the twist: this effect doesn't care which direction time flows. The same weird influence happens whether you're moving forward or backward in time, hinting that quantum mechanics might be fundamentally time-symmetric. This opens the door to retrocausality, the mind-bending possibility that future events could influence the past. Think of it like sending a letter to your younger self, but on a quantum scale. Experiments with delayed choice setups, where a particle's behavior seems to change based on measurements made later, add fuel to this fire. If quantum mechanics truly doesn't distinguish past from future, It challenges everything we assume about how events unfold. So what does this mean for our everyday reality? If time symmetry holds, the universe might be far more interconnected than we realize, with causes and effects blurring into a two-way street. It's a radical rethink of time's flow, and one that could reshape our understanding of everything from quantum computing to the very fabric of causality. But for now, let's keep exploring, because the mysteries of time's hidden dimensions are far from solved. Now, let's venture into one of the most dramatic distortions of time in the universe, the warping effect near black holes. Picture this: the immense gravity of a black hole doesn't just bend space, it twists time itself into something unrecognizable. If you could hover near the edge of a black hole, time for you would slow down drastically compared to someone far away. It's like standing next to a cosmic slow-motion button. A perfect example of this comes from the movie Interstellar, where the crew visits Miller's planet, orbiting a supermassive black hole named Gargantua. For every hour they spend on the planet's surface, 7 years pass back on Earth. While the movie takes some creative liberties, the science behind it is real. Einstein's theory of relativity predicts this extreme time dilation near massive objects, and black holes are the ultimate testing ground for these mind-bending effects. To visualize how black holes warp space-time, physicists use something called Penrose diagrams. These diagrams map out the paths light and matter can take near a black hole, showing how the event horizon, the point of no return, acts like a one-way door. Time and space switch roles inside, meaning falling toward the singularity isn't just moving through space, it's like traveling into the future with no way back. So what does this mean for our understanding of time? Black holes stretch the fabric of reality to its limits, revealing how fluid time truly is under extreme conditions. They're not just cosmic vacuum cleaners, they're natural laboratories for testing the wildest predictions of relativity. And as we peer deeper into their mysteries, we might just uncover new layers of time's hidden dimensions. Now, let's unravel another layer of time's mystery, one where the very fabric of reality might be stitched together by quantum entanglement. Imagine time not as a standalone dimension, but as something that emerges from the strange, invisible connections between particles across the universe. This is the heart of holographic time entanglement, a theory that blurs the line between space, time, and the quantum world. At the core of this idea is a groundbreaking connection known as ER equals EPR. It suggests that quantum entanglement, the spooky link between particles instantaneously affecting each other no matter the distance, might actually be tied to wormholes, the cosmic shortcuts through space-time. Think of it like this: when two particles are entangled, there could be a tiny, hidden wormhole threading them together, encoding their connection not just in space but in time itself. What makes this so mind-bending is the implication that time might not flow independently. Instead, it could arise from these intricate webs of quantum relationships. Picture a vast cosmic hologram where the universe's entire timeline is projected from a deeper, timeless reality. Wormholes, in this view, aren't just bridges across space, they could be tunnels through time, linking moments in ways we're only beginning to grasp. So why does this matter? If time truly emerges from entanglement, it could rewrite our understanding of causality, black holes, even the Big Bang. It's a radical shift, one that turns time from a backdrop of the universe into something far more dynamic, woven into the quantum code of reality itself. And as we explore these connections, we might just find that time's hidden dimensions are closer than we ever imagined. But what if the Big Bang wasn't the true beginning? Let's step even further back into the realm of theories that dare to ask what came before the universe as we know it. One of the most fascinating ideas comes from loop quantum cosmology, which suggests that the Big Bang might not have been a singular explosion from nothing, but rather a rebound from a previous universe that collapsed. Think of it like a cosmic bounce, a universe contracting down to an incredibly dense state before springing back outward in what we now call the Big Bang. This bouncing universe model flips the script on our traditional timeline. Instead of time starting at the Big Bang, it could stretch infinitely into the past with cycles of expansion and contraction. Even more intriguing is conformal cyclic cosmology, a theory proposed by Nobel laureate Roger Penrose. It proposes that our universe's distant future, a cold, empty expanse after heat death, could somehow reset into the next Big Bang, creating an endless loop of universes. Picture time not as a straight line, but as an infinite series of circles, each universe's end seeding the next's beginning. So why consider these ideas? They challenge the very notion of a definitive starting point. If time existed before the Big Bang, our understanding of creation, entropy, and even the arrow of time might need a radical overhaul. These theories don't just stretch the boundaries of physics, they invite us to rethink whether time ever truly begins or ends at all. And as we peer into these cosmic echoes, we might find that the universe's greatest mysteries lie not in its birth, but in what came before. Now let's shift our focus from the cosmic scale to something much closer to home, our own minds. Time might bend and stretch across the universe, but how do we actually experience it? Neuroscience and psychology reveal that our perception of time is far from objective. Think about those moments when an hour feels like a minute or a second drags on forever. That's your brain playing tricks with time. Einstein showed us that time is flexible, warped by gravity and motion, yet our daily experience feels rigid, a steady, unbroken flow. But why? It turns out our brains construct time like a story, stitching together sensory input, memory, and anticipation. Disorders like time agnosia, where people lose the ability to track time altogether, highlight just how fragile this perception really is. Imagine waking up with no sense of whether minutes or hours have passed, a disorienting glimpse into how deeply our minds shape reality. So what creates this illusion of flow? Some researchers point to the brain's internal clock, a network of neurons firing in rhythmic patterns. Others suggest it's a byproduct of how we process change, like frames in a movie blending into motion. Whatever the mechanism, one thing's clear: time as we feel it is a mental masterpiece, not a universal truth. And that raises a haunting question: if our perception can distort time so easily, how much of reality are we really seeing? Now let's take a step into one of the most mind-bending theories of all. What if time isn't a fundamental part of reality, but something generated by a cosmic computer? This is the core idea behind the digital physics hypothesis, which suggests our universe might be a vast simulation running on some unimaginable hardware. If that's true, then time as we know it could simply be the ticking of this grand machine's clock. Think of it like a video game where the world only updates in tiny, discrete steps, each frame rendering the next moment. In this view, time wouldn't flow smoothly but would jump from one computational state to another, like pixels lighting up on a screen. Some scientists even point to cellular automata, simple programs where grids of cells evolve step by step based on set rules, as a possible blueprint for how reality itself might compute existence. The implications are staggering. If time is just computation, then the smooth, continuous experience we perceive could be an illusion, a trick of the simulation's processing speed. It raises wild questions. Who's running the program? Could the simulation ever glitch or reset? And if time is just data, does that mean the past and future are already stored somewhere, waiting to be rendered? Whether or not the digital physics hypothesis holds up, it forces us to rethink time in a way that's as unsettling as it is fascinating. Now, let's shift gears to something equally mind-bending: how time itself might be uncertain at the smallest scales. This is where the time-energy uncertainty principle comes into play, a fascinating twist on the quantum world's famous uncertainty principle. You've probably heard that in quantum mechanics, we can't precisely know both a particle's position and momentum at the same time. But here's the kicker: there's a similar trade-off between time and energy. What does that mean? Imagine the universe as a restless, bubbling sea at the tiniest levels. Particles and energy flicker in and out of existence so quickly that time itself becomes fuzzy. These fleeting bursts are called virtual particles, and they're not just theoretical. They've been detected in experiments like the Casimir effect. They pop up, borrow energy from the vacuum of space, and vanish almost instantly, all thanks to the time-energy uncertainty principle. This chaotic dance creates what physicists call space-time foam, a frothy, churning landscape where even the fabric of reality isn't smooth but filled with microscopic fluctuations. It's as if time itself stutters at these scales, blurring the line between moments. Some theories suggest these quantum jitters could hint at hidden dimensions of time, where the very flow we experience might be an average of countless tiny, uncertain ticks. Whether or not that's true, one thing's certain: the closer we look at time, the stranger it gets. Now, let's take a step back and consider something even more profound. Why does time behave the way it does in the first place? This brings us to the anthropic principle, a thought-provoking idea that suggests the laws of our universe, including time's arrow, might be fine-tuned just right for life to exist. Think about it. If time flowed backward, or if entropy didn't increase, could complex structures like stars, planets, or even us ever form? The anthropic principle argues that we observe time moving forward simply because we're here to observe it. In other words, if time worked differently, life as we know it wouldn't exist, and no one would be around to question it. But here's where it gets wild. What if our universe isn't the only one? Some theories propose a vast multiverse where countless universes exist with their own unique laws of time. Maybe in some, time loops endlessly, while in others it stands completely still. We just happen to live in the one where time's rules allow for galaxies, biology, and conscious beings. Of course, this raises big questions. Is our experience of time just a cosmic coincidence, or is there a deeper reason behind it? Could other universes with different temporal laws even be testable, or are they forever beyond our reach? Whether you find the anthropic principle satisfying or unsettling, one thing's clear: it forces us to rethink time not just as a physical phenomenon, but as something deeply connected to the very possibility of existence itself. Now let's flip the script literally. Imagine a hidden dimension where time runs backward, like a reflection in a cosmic mirror. This is the heart of the time mirror theory, a mind-bending idea that suggests antimatter might not just be matter's opposite, it could be matter moving in reverse through time. At the core of this theory is something called CPT symmetry, a fundamental rule in physics that combines charge, parity, and time. Here's the gist: if you take a particle, flip its charge to its antimatter counterpart, mirror its position in space, and reverse its time direction, the laws of physics should stay the same. This symmetry hints that antimatter might behave exactly like ordinary matter if time flowed backward. Think of it like watching a movie in rewind. A particle moving forward in time could appear as its antiparticle moving backward. Some experiments even suggest this might be more than just a neat idea. For instance, when particles and antiparticles collide, they annihilate in a burst of energy, almost as if they're canceling each other out across time. But here's the twist: if antimatter truly is time-reversed matter, why doesn't the universe have equal amounts of both? Some physicists argue that hidden, mirror-time dimensions could explain this imbalance, with antimatter hiding in a parallel temporal layer. Others wonder if this could unlock new ways to test time's deepest mysteries, like whether the past and future are more connected than we realize. Whether the time mirror theory holds up or not, it challenges us to see time not as a one-way street, but as a two-way mirror, where the future might just be the past looking back at us. Now let's zoom in and out on an idea that makes time feel less like a straight line and more like an intricate, repeating pattern. The fractal time hypothesis suggests that time doesn't just flow uniformly. It operates in nested layers, echoing itself at different scales, much like the infinite complexity of a Mandelbrot set. Picture a coastline. The closer you look, the more detailed and self-similar it becomes. Fractal time works the same way. A single moment might contain smaller, faster cycles of time within it, while also being part of a larger, slower rhythm. This isn't just poetic. It could explain why certain phenomena, from cosmic events to stock market fluctuations, seem to repeat in recognizable patterns across different time frames. In cosmology, this idea might help unravel mysteries like the large-scale structure of the universe. Galaxies aren't randomly scattered. They form filaments and voids that look eerily similar whether you're observing a few million light years or the entire observable universe. Could fractal time be the hidden framework behind this cosmic symmetry? Even in finance, traders have noticed that market trends often mirror themselves across days, months, or years, like a fractal repeating its shape. Some researchers argue this isn't just coincidence, but a hint that time's nested layers influence how systems evolve. Of course, the big question remains: is fractal time a real feature of the universe or just a useful metaphor? Either way, it pushes us to see time not as a smooth river but as a cascading waterfall with currents within currents, each revealing new layers of the mystery. But here's where things get even stranger. What if time itself doesn't flow unless someone is there to observe it? This brings us to our final theory, the conscious observer effect, a mind-bending idea that suggests time's passage isn't just something we experience, but something we might actually create. Think about quantum mechanics, where particles exist in a haze of possibilities until measured. The act of observation collapses these possibilities into a single reality. Now scale that up. Could the entire universe be waiting for conscious observers to pin down time, making it flow from one moment to the next? Some physicists argue that without consciousness, time might simply freeze like a paused movie. Then there's the Boltzmann brain paradox, a wild thought experiment where a self-aware entity could randomly form from chaotic particles, complete with false memories of a past. If such a thing is possible, how do we know our own experience of time isn't an illusion? Philosophical idealism takes this further, proposing that reality itself is mental, and time is just a construct of our collective perception. But here's the kicker: if consciousness shapes time, does that mean the universe is somehow aware? Or is time's flow more like a dance between the observer and the observed? Whether you find this idea profound or unsettling, it forces us to confront a humbling possibility, that the ticking clock in your head might not just measure time, but help bring it into existence. And with that, we've reached the end of our journey through 30 theories that stretch, twist, and reimagine time itself. Which one resonates with you? Drop your thoughts in the comments below, and don't forget to subscribe for more mind-expanding deep dives into the universe's greatest mysteries. As we wrap up this exploration of time's hidden dimensions, one thing becomes undeniably clear: our universe is far stranger and more mysterious than we ever imagined. From the static block universe to the mind-bending conscious observer effect, each theory we've uncovered today flips our everyday understanding of time on its head. Some paint time as an illusion, others as a layered dimension, and a few even suggest it might not exist at all without us to perceive it. What's remarkable is how these ideas, though wildly different, all push the boundaries of science and philosophy. They force us to question not just the nature of reality, but our very place within it. Whether you're drawn to the elegance of eternalism, the paradoxes of time loops, or the radical idea that consciousness shapes time itself, there's no denying that each theory offers a unique lens to view the cosmos. So now it's your turn. Which of these 30 theories resonates with you the most? Do you see time as a river, a tapestry, or something even more extraordinary? Drop your thoughts in the comments below, and let's keep the conversation going. If you enjoyed this deep dive into the universe's greatest mysteries, don't forget to hit that subscribe button and ring the notification bell. There's always more mind-expanding content on the horizon, and you won't want to miss what's coming next. Thanks for joining me on this journey through the hidden dimensions of time. Until next time, keep questioning, keep exploring, and keep wondering about the incredible universe we call